In the last video, I talked about how voltage is useful for quantifying the energy change associated with moving a charge from place to place. Another parameter that's associated with energy transfer is the rate at which charge is moving. That's called current, and it's the subject of this video. Current is simply the rate of change of charge with time. Mathematically, it's the derivative of charge with respect to time, dq by dt. The units of current are amperes, or amps for short, and they're represented by a capital letter A. Since units of charge are coulombs and time is measured in seconds, amperes are equivalent to coulombs per second. Current, then, is the number of coulombs of charge that pass a point every second. As with voltage, we need a sign convention for current. The direction of positive current is indicated by an arrow on our circuit diagram. As with voltage, completely specifying a current requires a magnitude and a sign convention as indicated by the arrow. Since the magnitude can be either positive or negative, the arrow tells us how to interpret the sign. Changing the direction of the arrow reverses the sign on the current. For example, I have a 3 amp current as indicated here. The arrow tells me how to interpret the sign of the current. Since the current is a positive 3 amps, this current flows in the same direction as the arrow. Another example is shown here. This current has a magnitude of negative 3 amps. The arrow indicates that the direction of positive current is now to the left. Switching the direction of the arrow changes the sign of the current value, so negative 3 amps to the left is the same as positive 3 amps to the right. So the two currents shown here are the same. Next, I'll show how the sign convention affects the measurement of currents. To demonstrate sign conventions, I'll measure the current this battery can provide. I can measure the current through the element with this digital multimeter. The DMM has a sign convention for current. Current entering the red terminal and leaving the black terminal is displayed as positive. If the current enters the black terminal and leaves the red, a negative value is displayed. This corresponds to setting a sign convention with an arrow entering the red terminal. Now, if I connect the probes with the red terminal at the positive terminal of the battery, I get a positive current. If I switch the terminals, the sign on the current changes. There is one property of all of our circuit elements that will affect how we interpret currents. None of our circuit elements will be able to accumulate or store charge. That means that any charges entering an element must be balanced by an equal amount of charge leaving the element. So if I have a current I entering this terminal of an element, I need to have an equal current leaving the other terminal of the element. Since changing the arrow direction corresponds to a change of sign, I can also express this as a current with the opposite sign entering the other terminal of the element. Finally, there's one point that I can't overemphasize. Voltage is an energy level difference between two different points in a circuit, while current is a charge flow past a single point in a circuit. Now that we've got the basic parameters associated with energy transfer taken care of, let's take a look at circuit elements that can be used to get the energy where we want it to be. The next video is associated with mathematically modeling the circuit elements.